Greetings, Panthers. In the last video, we talked about how to find the concentration of a solution using a term called molarity. And in this video, we're going to talk about how to dilute solutions. So last time we showed you how to measure out a certain amount of compound, for example, sodium chloride or sodium hydroxide or something like that. And we talked about how to then figure out what the concentration of that solution is. And making solutions is a little bit tedious. I mean, you have to really carefully measure out the masses, really carefully measure the volumes. So a lot of times what we do is rather than just making a solution every single time with a set molarity, we actually do something like we make one solution, usually in a big volumetric flask. So maybe something like a 4-liter volumetric flask. So a large volumetric flask, we might make a solution of our compound or of material, whatever it is we want. And then if we want, we can then say, all right, I want to make another solution, maybe only 100 milliliters of the other solution. And what we typically do is we make a higher concentration solution initially. So let's say this is something like, in the example we have here, 4.38 molar, and this is a calcium nitrate solution. Okay, so this problem is how would you prepare 100 milliliters of a 2.35 molar calcium nitrate solution starting with a 4.38 molar stock solution. So what we do, we call this high concentration solution, the one we've made a lot of it, we call this a stock solution. This is sort of like if you have your sweet tea, that's the container in the store, and then if you want to dilute it after that, you can always add water to that. So we start with a high concentration, and then we transfer some of that out of the high concentration solution into another volumetric flask, in this case a 100 milliliter volumetric flask. And then we add water to this up to the fill line, and that will make a more dilute solution. And we can do that in a very controlled way by knowing the molarities and being able to calculate the dilution effect. We can do this with a very simple equation. M initial times V initial is equal to M final times V final. Now what I mean by M initial is the initial molarity times the volume initially is equal to the final molarity times whatever the final volume is. Now if you look at that equation carefully and you think about what I said those terms mean, if we take M initial times V initial, this is equal to the number of moles. Remember before we said whenever you have molarity times volume, it's equal to the number of moles. So this is saying number of moles is equal to number of moles. And this should make sense. When you dilute something, you're not losing or gaining any amount of whatever the thing is you're looking at, but you're just changing the volume that it's in. So let me give you an example of this. This is kind of a ridiculous example, but suppose you have a glass of grape juice. And whatever makes up grape juice, grape juicium, is in this grape juice container at a certain concentration. So your glass might be, say, 200 milliliters or 300 milliliters, and whatever the molarity of grape juicium is, that's what you have in your glass. And suppose we took this glass and then dumped it into a swimming pool. Now the lifeguards may not appreciate it, or the owner of the pool may not appreciate you dumping grape juice into the pool, but what would happen is the number of moles of grape juicium would be exactly the same in your cup as it is in the swimming pool. What would change? Well, the volume would go way, way, way up because the swimming pool has a massive volume compared to your cup, and the molarity would go way, way down, but you'd still have the same number of moles. So this equation, M initial V initial equals M final V final, is the equation that we want to use for dilution problems, whenever you're trying to dilute a substance. So we can have a problem that looks something like this. How would you prepare 100 milliliters of a 2.35 molar calcium nitrate solution starting with a 4.38 molar stock solution? Notice it doesn't say how much of that there is. There can be any amount of the stock solution. So in my picture over here, I've got 4 liters of the stock solution, and I'm trying to make 100 milliliters of my calcium nitrate solution. All right, so let's just sort of start working our way through this problem. M initial, V initial, M final, V final. See what we have in my problem here. So the initial molarity is the concentration of the stock solution, 4.38 molar. The initial volume, well, I don't know. I'm trying to figure out how much of that I need. The final volume, or excuse me, final molarity is 2.35 molar. and the final volume is 100 milliliters. So we can write an equation that looks something like this. M initial, V initial equals to M final, V final, and I'm trying to find V initial. So I'm going to rearrange this equation to say V initial is equal to M final times V final divided by M initial. And just a word of advice to you, if you're solving a problem where you have to plug things in, I recommend solving for the variable first before you plug things in. Then you can kind of see what's happening with the units and make sure they're canceling each other out correctly. So V initial is going to equal to M final, 2.35 molar, times V final, 100 milliliters, times 1 liter for every 1,000 milliliters. Milliliters are going to cancel milliliters, divided by 4.38 molar. And this is molar calcium carbon or calcium nitrate for both cases. So molarity is going to cancel molarity. So my only unit that's left is liters. So when we do this calculation, this comes out to be 0.0537 liters. I want to find out how many milliliters this is going to take. So I'm going to multiply times 1,000 milliliters divided by 1 liter. Once again, liters cancel liters. And I'm going to get 53.7 milliliters. All right, so what does this mean experimentally? How do we actually do this experiment? So, and really, what does that 53.7 mean? That is 53.7 of the 4.38 molar solution. So in my picture up here, I'm going to take out 53.7 milliliters of the stock solution. So I'm going to somehow, probably with a graduated cylinder or maybe with a burette, I'm going to measure out 53.7 milliliters of this stock solution, and I'm going to put that into a 100 milliliter volumetric flask. Remember, volumetric flasks are calibrated. You pick a certain one out, in this case 100 milliliters. You pick 100 milliliters out, and I'm going to put 53.7 milliliters of the stock in there, and then I'm going to add on top of that water. And I'm going to fill the water right up to the line and put the lid on it, shake it up, and after I shake it up and I'm convinced that I have a uniform solution, I now have a 2.35 molar solution of calcium nitrate. Okay, that's our general strategy. We remove it from the stock solution, put that amount in the volumetric flask, and fill to the line, and now I have a lower concentration solution. You can do a series of these. They're called serial dilutions, where we might take out 10 milliliters out of here, 10 milliliters out of here, 10 milliliters out of here, and you could do a series of, factor of 10 dilutions. But you use the exact same equation, M initial, V initial equals M final, V final. By the way, some of you might be in biology classes, and you might have had an equation that looks like this. C initial equals V initial times C final times V final. That C is just generic. It just means concentration. This is specific for molarity, but you can really use any concentration unit and do this dilution process. All right, let's take a look at one more problem, which is worded a little bit differently. It's a little bit odd, but as you can see, knowing our knowledge of molarities, how we can solve this type of problem. So we have a concentration example. What is the molarity of the resulting solution produced by mixing 50 milliliters of a 0.2 molar sodium chloride solution followed by 100 milliliters of a 0.1 molar sodium chloride solution? So this is not a crazy problem. This is saying I've got two different solutions. One of them I have a certain amount, 50 milliliters, 0.2 molar, and then the other one I have a different amount, 100 milliliters, 0.1 molar. So let's call this solution A under these conditions, and we'll call this solution B under these conditions. Now, it's asking for the molarity. So we know that molarity is equal to number of moles divided by liters of solution. In this case, it would be moles of NaCl. So if you want to stop your video and see if you can figure out this problem, we'll come back in a second and work on the strategy for this. Okay, so here's the strategy. We need to find the total number of moles of these two solutions, and we also need to find the total volume of these solutions. If we have the total moles and the total volume, then we can find the molarity. So the total volume is easy. This is just the sum of the two volumes. So if we add solution B volume, 50 milliliters, plus solution A volume, 100 milliliters, that's going to equal to 150 milliliters is my total volume. Okay, that's easy. Total number of moles is going to equal to the moles coming from solution A plus the moles coming from solution B. All right, so how do we find moles of solution A? Well, this is just like a few other problems we've done before. Moles of solution A is equal to molarity times volume. So I'm going to say molarity of solution A times the volume of solution A, which is equal to 50 milliliters times 1 liter for every 1,000 milliliters. Remember, we always need to convert milliliters, and we'll just cross these units off to make sure we're doing that, times 0.200, and I'm going to write the units out completely. Moles NaCl for every 1 liter of solution. So those are going to cancel now, liters of solution. And when we do this calculation, this comes out to be 0.0100 moles NaCl. Okay, 3 significant figures. So 0.01 moles of NaCl is coming from solution A. How about the number of moles of solution B? That's also equal to molarity of B times volume of B, which is equal to 100 milliliters times 1 liter for every 1,000 milliliters. Cross off the units. Times, now our concentration is 0.1 molar, not 0.2 molar. So this is going to be 0.100 moles NaCl for every 1 liter of solution. Liter of solution is going to cancel liter of solution, and this actually also happens to be 0.100 moles of NaCl. So my total number of moles and total is equal to 0.0100 plus 0.0100 moles, or in other words, 0.0200 moles NaCl. So the molarity of my solution, molarity of this new resulting solution by pouring these two things together, is the total number of moles, 0.022 moles NaCl, divided by the total volume, 0.1500 liters. And that comes out to be 0.133 molar NaCl. That's also the same as 0.133 moles NaCl per 1 liter of solution. Okay, couple of important points. You do not need a liter in order to find the molarity. You just need to know the volume and the number of moles in that volume. So the other thing you can note from this particular problem is, do you notice the two different molarities were 0.2 molar for one of the solutions and 0.1 molar for the other solution, and the resulting molarity is 0.133. It makes sense. If you dump two solutions in with different concentrations, your new molarity should be somewhere in between those two concentrations. So this one comes out to be 0.133 molar. Okay, that's a good place to stop. Thanks for watching, and look forward to seeing you again. Bye.